Hello friends, previously we discussed that the induction of a current by a changing flux means that energy is being transferred to that current and EMF is induced by a changing magnetic flux even if the loop through which the flux is changing is not a physical conductor but an imaginary line. And finally, we proved that the changing magnetic field induces an electric field at every point of such a loop. In today's lecture, we shall be discussing the self and mutual inductions, inductors and inductance. We earlier learned that a capacitor can be used to produce a desired electric field. We considered the parallel plate arrangement as a basic type of capacitor. Similarly, an inductor can be used to produce a desired magnetic field. We shall consider a long solenoid as our basic type of inductor. If we establish a current I in the windings of the solenoid which we are taking as our inductor, the current produces a magnetic flux through the central region of the inductor. The inductance of the inductor is then defined in terms of that flux as L is equal to N phi B divided by I. Here N is the number of turns. The windings of the inductor are said to be linked by the shared flux, and the product of turns and magnetic flux is called the magnetic flux linkage. The inductance L is thus a measure of the flux linkage produced by the inductor per unit of current. Inductance of a solenoid. Consider this long solenoid of cross-sectional area A. If we use defining equation L is equal to N phi B upon I to find the inductance per unit length near its middle, we must calculate the flux linkage set up by a given current in the solenoid windings. Consider a length L of the solenoid near the middle. The flux linkage there is N phi B equal to NL into BA. Here N is the number of turns per unit length of the solenoid and B is the magnitude of the magnetic field within the solenoid. The magnitude B is given by B is equal to mu0 I N. So from equation A, L is equal to NL into BA divided by I, which again becomes equal to NL into mu0 IN into A divided by I. So L is equal to mu0 N square LA. Thus, the inductance per unit length near the center of a long solenoid is capital L upon small l is equal to mu0 N square into A. Inductance, like capacitance, depends only on the geometry of the device. The dependence on the square of the number of turns per unit length is to be expected. If you say triple N, you note only triple the number of turns, but you also triple the flux through each turn, multiplying the flux linkage and thus the inductance L by a factor of 9. Self-induction. If two coils, which we can now call inductors, are near each other, a current I in one coil produces a magnetic flux through the second coil. We have seen that if we change this flux by changing the current, an induced EMF appears in the second coil according to Faraday's law. An induced EMF appears in the first coil as well. This process is called self-induction, and the EMF that appears is called a self-induced EMF. It obeys Faraday's law of induction just as other induced EMFs do. For any inductor, equation A tells us that N phi B is equal to Li, and Faraday's law tells us that epsilon L is equal to d n phi b upon dt. By combining these two equations, we can write epsilon L is equal to minus L di upon dt, which is the self-induced EMF. Thus, in any inductor, such as a coil or a solenoid, a self-induced EMF appears whenever the current changes with time. The magnitude of the current has no influence on the magnitude of the induced EMF. Only the rate of change of the current counts. Direction of self-induced EMF. You can find the direction of a self-induced EMF from Lenz's law. Epsilon L is equal to minus L di upon dt. The minus sign in equation B indicates that, as the law states, the self-induced EMF has the orientation such that it opposes the change in current I. We can drop the minus sign when we want only the magnitude of EMF. Suppose that you set up a current I in a coil and arrange to have the current increase with time at a rate di upon dt. In the language of Lenz's law, this increase in the current in the coil is a change that the self-induction must oppose. Thus, a self-induced EMF must appear in the coil, pointing so as to oppose the increase in the current, trying but failing to maintain the initial condition as shown in figure A. If instead the current decreases with time, the self-induced EMF must point in a direction that tends to oppose the decrease as shown in figure B, again trying to maintain the initial condition. Electric potential. Earlier we saw that we cannot define an electric potential for an electric field that is induced by a changing magnetic flux. This means that when a self-induced EMF is produced in the inductor as shown, we cannot define an electric potential within the inductor itself where the flux is changing. However, potentials can still be defined at points of the circuit that are not within the inductor, points where the electric fields are due to charge distributions and their associated electric potentials. Moreover, we can define a self-induced potential difference across an inductor. For an ideal inductor, that is, its wire has negligible resistance, the magnitude of potential difference is equal to the magnitude of the self-induced EMF. If instead the wire in the inductor has resistance R, we mentally separate the inductor into a resistance R and an ideal inductor of self-induced EMF. As with a real battery with EMF and internal resistance, the potential difference across the terminals of a real inductor then differs from the EMF. Unless otherwise indicated, we assume here that inductors are ideal. Energy stored in a magnetic field. When we pull two charged particles of opposite signs away from each other, we say that the resulting electric potential energy is stored in the electric field of the particles. We get it back from the field by letting the particles move closer together again. In the same way, we say energy is stored in a magnetic field, but now we deal with current instead of electric charge. To derive a quantitative expression for that stored energy, consider this figure, which shows a source of EMF connected to a resistor R and an inductor L. According to loop rule equation, epsilon is equal to L di upon dt plus IR, which is the differential equation that describes the growth of current in this circuit. Recall that this equation follows immediately from the loop rule, and the loop rule in turn is an expression of the principle of conservation of energy for single loop circuits. If we multiply each side of equation by I, we obtain epsilon I is equal to Li di upon dt plus I square R, which has the following physical interpretation in terms of the work done by the battery and the resulting energy transfers. If a differential amount of charge passes through the battery in time dt, the battery does work on it in the amount epsilon dq. The rate at which the battery does work is epsilon I. Thus, the left side of equation C represents the rate at which the EMF device delivers energy to the rest of the circuit. The rightmost term in equation C represents the rate at which energy appears as thermal energy in the resistor. Energy that is delivered to the circuit but does not appear as thermal energy must, by the conservation of energy hypothesis, be stored in the magnetic field of the inductor. Because equation C represents the principle of conservation of energy for RL circuits, the middle term must represent the rate at which magnetic potential energy is stored in the magnetic field. Thus, dUp upon dt is equal to Li into di upon dt. We can write this as dUb is equal to Li into di. Integration yields integral of dUb from 0 to ub is equal to integral of Li di from 0 to I, or ub is equal to half Li square, which represents the total energy stored by an inductor L carrying a current I. Energy density of a magnetic field. Consider a length L near the middle of a long solenoid of cross-sectional area A carrying current I. The volume associated with this length is Al. The energy stored by the length L of the solenoid must lie entirely within this volume because the magnetic field outside such a solenoid is approximately zero. Moreover, the stored energy must be uniformly distributed within the solenoid because the magnetic field is approximately uniformly everywhere inside. Thus, the energy stored per unit volume of the field is small ub is equal to capital UB upon Al, or since capital UB is equal to half Li square, we have small ub is equal to Li square upon 2Al, which is equal to capital L upon small l into I square divided by 2A. Here L is the inductance of the length L of the solenoid. Substituting for capital L upon small l from this inductance equation of solenoid, we find small ub is equal to half mu 0 n square I square. Here n is the number of turns per unit length. From the equation of net current in terms of magnitude of the uniform field B is equal to mu 0 In, we can write this energy density as small ub is equal to B square upon 2 mu 0. This equation gives the density of stored energy at any point where the magnitude of the magnetic field is B, even though we derived it by considering the special case of a solenoid. This equation holds for all magnetic fields, no matter how they are generated. Mutual induction. In this section, we return to the case of two interacting coils, which we discussed when we were discussing Faraday's law, and we treat it in a somewhat more formal manner. We saw earlier that if two coils are close together, a steady current I in one coil will set up a magnetic flux through the other coil, or we could say establish a link with the other coil. If we change I with time, an EMF given by Faraday's law appears in the second coil. We called this process induction. We could better have called it mutual induction to suggest the mutual interaction of the two coils and to distinguish it from self induction, in which only one coil is involved. Let us look a little more quantitatively at mutual induction. This figure here shows two circular close packed coils near each other and sharing a common central axis. With a variable resistor set at a particular resistance R, the battery produces a steady current I1 in coil 1. This current creates a magnetic field represented by vector B1. Coil 2 is connected in a sensitive meter but contains no battery. A magnetic flux phi 21, the flux through coil 2 associated with the current in coil 1, links the N2 turns of coil 2. We define the mutual inductance M21 of coil 2 with respect to coil 1 as M21 is equal to N2 into phi 21 divided by I1, which has the same form as L is equal to N phi upon I, the definition of inductance. We can then recast equation D as M21 into I1 is equal to N2 into phi 21. If we cause I1 to vary with time by varying R, we have M21 into dI1 upon dt is equal to N2 into d phi 21 upon dt. The right side of this equation is, according to Faraday's law, just the magnitude of the EMF appearing in coil 2 due to the changing current in coil 1. Thus, with a minus sign to indicate direction, epsilon 2 is equal to minus M21 into dI1 upon dt. Let us now interchange the roles of coil 1 and 2 as in figure. That is, we set up a current I2 in coil 2 by means of a battery, and this produces a magnetic flux phi 12 that links coil 1. If we change I2 with time by varying R, we then have, by argument given earlier, epsilon 1 is equal to minus M12 into dI2 upon dt. Thus, we see that the EMF induced in either coil is proportional to the rate of change of current in the other coil. The proportionality constants M21 and M12 seem to be different. However, they turn out to be the same, although we cannot prove the fact here. Thus, we have M21 is equal to M12, which is equal to M, and we then can write epsilon 2 is equal to minus M into dI1 upon dt, and epsilon 2 is equal to minus M into dI2 upon dt. So friends, here we come to the end of our discussion in this lecture today, and therefore we sum up. An inductor is a device that can be used to produce a known magnetic field in a specified region. If a current I is established through each of the n windings of an inductor, a magnetic flux links those windings. If a current I in a coil changes with time, an EMF is induced in the coil. If coil 1 and 2 are near each other, a changing current in either coil can induce an EMF in the other. So that is it for today. See you in the next lecture where we shall be discussing more about magnetostatics. Thank you very much.